Okay, thanks to the organizers for inviting me to be here. I enjoy being here. A great place, and I hope to interact, have interesting conversations with all of you here. So I chose this topic of talking about looking at the SKA era and going beyond. What are the challenges and opportunities that we can think of for innovation in imaging and cosmology and other fields as well. So this is a bit of a deviation from the previous two speakers. So I will touch upon several other topics as well. So we're going to hear quite a few talks on how challenging things are. And sometimes I've been in that camp too, and I've been in a little pessimistic mood and gone into being pessimistic. But recently I've started thinking about these challenges as actually opportunities. And then I felt like quite excited to be working on several of these topics. So hopefully by the end of this talk, you will have some uplifting message from this talk. I will touch upon these topics. Of course, EOR is a prime topic. I will also touch upon a little bit about the time domain and data intensive astronomy in the SK era. And of course, some conventional traditional topics like imaging, calibration, RFI, what the opportunities, challenges and opportunities are. So of course, this is one of the key science or dominant science topic for SKA and other instruments currently operating. Here we're interested in reconstructing the ionization history of the universe, which of course has unique spectral signatures depending on lots of a variety of astrophysical processes and cosmology as well. And the potential for 21 centimeter results have been known for quite a while. They can provide exquisite astrophysical constraints independent of other experiments out there. And they can also provide or decouple some of the degeneracies in cosmology parameter space as well. So I won't dwell too much into this topic. But what are the challenges? As we've seen, we've heard in the previous two talks, the foregrounds are very bright, and this kind of propagates into a whole lot of other challenges. Basically, the challenges of the spectral dynamic range, and that also translates to a huge challenge in calibration. And we've known this for a while, for more than a decade, with different simulations, with different instruments. We've known that we need a calibration accuracy to better than 1 part in 10 to the power 5 or even more. And we've already heard some very exciting developments in calibration. Hera follows a different calibration scheme called the redundant calibration. We've heard a bit about the calibration strategy for LOFAR, and probably looking at some other hybrid calibration schemes going forward. And there's been a lot of work that's been happening, and we've started seeing the fruits of that work. The Hera results have been improving. We've got significant constraints. In fact, astrophysically meaningful constraints as well. And we just heard from Leon about the recent LOFAR results, which have also started becoming quite tight and astrophysically meaningful. There's also MWA results expected soon. They're under review, and can't say much about it, but from the last I heard, it's going to be a significant improvement as well from the MWA. So there have been gradual but very steady improvements. And we've got different experiments with different approaches. We've seen LOFAR is improving its results, but limitations coming from possible beam errors and incomplete foreground removal, for example. Hera has also been improving its results, but its main limitation seems to be from inter-antenna coupling effects, that are hard to remove. And MWA is also improving results, but has a different kind of limitation, which is coming from its sharp bandpass structures. So it's all good because they have independent set of constraints to going towards the same direction. So as we've come to expect now, supposing we detect, or we say we detect something, how are we going to believe what we've detected is true? And as Leon said, there's not going to be any instant satisfaction. We're still going to be skeptical. It's going to take a while before it becomes real for us. So this is where the power of completely independent experiments is very important in an important experiment like this. So I want to bring a bit of attention to the 21 centimeter forest through absorption. And this has been known to be very powerful, proposed over 20, 25 years ago. But I don't know if we've sort of forgotten talking about this in much detail, because to see a 21 centimeter forest in absorption, the requirement is that the background source has to be extremely bright. So, and that's hard to come by. We don't have that many bright background sources at these high redshifts. There might be a few, you might get lucky, but we cannot expect to have enough number of sight lines with very bright sources. However, so this is the picture we're looking at. We have a bright background source, and we are looking through the neutral and the ionized medium here, and we expect some absorption features here. So what is possible, though, is that even if you don't have a single or a few bright background sources, we can expect a lot of faint background sources, and we could do a statistical power spectrum along that line of sight and be able to come up with some kind of constraints. And here's is a paper that is some work that I did a while ago that shows that it is indeed possible with modern SKA-like arrays and arrays further in the future to be able to detect this 1D power spectrum along the line of sight, along specific lines of sight in a statistical sense. And they have the power to distinguish between a whole bunch of models. And I've also seen that the sample of such brighter radio quasars is also growing. So hopefully we could take this up as an alternate means to studying the same thing. I think it's quite prospective. This is also speaking to my own work. As we've seen, there's quite a bit of a challenge in calibration. And so we were motivated to think about some calibration independent ways of looking at the data. One such idea that comes to mind is obviously the well-known closure phase that has been known in radio interferometry for quite a while, where if you have a set of 3 antennas and you look at the triple product of the visibilities and the phase of that, that is completely independent of at least most of the calibration terms to first order. And so then when we started looking at what are we looking to detect in such a metric or such a statistic, is that the normal way of thinking about it is you look at visibility, spectra, and then you got some fluctuations on top of that. So here's like 3 visibilities modeled for 3 baselines, and the H1 spectra show as fluctuations on top of this. But it's the same thing, the same data, you could think of it as having been made up of a closure phase, which is the predominant phase coming from the foregrounds. And then if you add H1 on top of that, it's going to cause some kind of fluctuations here as well. So you could be looking at, again, the same kind of problem, which is a smooth spectrum with some fluctuations. And we could be trying to look for looking for spectral signatures in this particular quantity as well. What is the advantage? We can do very simple processing here. There's not no need for extensive calibration required. So we could, in principle, work with as close to the raw data as possible. And so you can see that it's the same idea, but a different quantity. So we did indeed do a bit more data analysis with this work. So this is some preliminary results that we had from HERA data a while ago, setting some upper limits with not too much of data, but maybe about 20 hours of data or something. And here's similar work extended to the MWA, and we're still quite a way to go down, but we hope that with more data, we should be able to get significantly better than what we have at the moment. But at the moment, these are noise limited. Of course, we don't know what we're going to hit as we dig deeper into the data, but this is another prospective direction to look into as an independent way to look at EOR. So then I thought of moving to the other domain, time domain and data-intensive astronomy. So we are looking at several arrays of this kind, made up of thousands and tens of thousands of elements. And this is, again, going to pose a lot of challenges for us, especially with multi-scale, hierarchical spatial scales involved. And when we look at the time domain astrophysics, for example, we are looking at extremely explosive phenomena occurring on very short time scales, milliseconds or less, for example. And to localize them and understand their origins is extremely important, and it could be extremely revealing about the universe. And what we require here, for example, is wide fields of view, so to catch as many of these events as possible. And we want a large collecting area made up of large number of elements and very high time resolution, being able to write the data quite fast outside of it. So all this points to very large number of elements with high time resolution, large field of view, and so on, the kind of experiments that I've shown here. While this is a great opportunity, the challenge is that the processing is going to be extremely challenging. The conventional way of thinking about processing these is to form pairs of correlations between every possible pair of elements. And then we've constructed our visibilities in the aperture plane. The idea is to invert them to the image plane here. But this is an order n square complex operation. And so with larger number of elements, this is going to become very extremely prohibitive. So the idea is that can we think about a different architecture to do the same thing, fundamentally changing the way we process data. So in nature, what usually happens is not what we do here. This is a rather indirect way of going about it. In nature, the light just comes and propagates through and does its superposition interference. And eventually we, for example, would be measuring the intensities, right? Like in a camera, for example. So can we emulate this particular architecture as opposed to working in the aperture plane? Can we directly do our camera type interferometry here? And the architecture is, the mathematics is quite simple. So what we do as correlating first and then Fourier transforming, we know very well from Fourier transform theory that is equivalent to doing the Fourier transform first, which is this propagation to the image plane of the waves as they come through, and then squaring it in the image plane. So mathematically identical, but the order of operations is quite different. And so what would be a traditional correlator, for example, where you do the order n square correlation, that would be your limiting factor. In here, that's going to change to a Fourier transform operation first, which would be the limiting factor. And then squaring can be done squaring and accumulation can be done at a slower pace. So we are fundamentally thinking of changing the architecture here, going from an order n square operation to possibly order n log n using NFFT. So this can be extremely rewarding for dense and large apertures. So such an architecture has been implemented on the long wavelength array in New Mexico using GPUs. And what was possible earlier was about 1 second was the fastest cadence we could work with. And with this particular system implemented, we brought it down to about 80 milliseconds, so a factor of more than 10 there. And this particular mode has been made available for users on a commensal basis as well. So when we look at the SK type arrays or even beyond, there are different parameters for the layout. Number of antennas in a station, the station size, the size of the element, the accumulation time scale that we're interested in, so on. These parameters determine what's the best strategy for processing the data. There's different places where different strategies take over, and at least for the nominal parameters that we've chosen here for SKA low-like station, it seems like this kind of a direct imaging architecture could be extremely beneficial. So maybe SKA is right now focused on its getting its operations ready, and maybe this is not the time for it, but at least a future version or future upgrade of SKA or other instruments should think of alternate processing architectures. And yeah, there's so many ways that we can customize this architecture there's just like so many elements available in the core, and we can massage it in so many different ways. And we've noticed that the GPU implementation that I talked about has some severe memory bandwidth limitations because of the 2D FFT and then the way the data moves around. And we believe that a FPGA-based implementation could overcome some of those limitations, especially related to FFTs. It can be done extremely efficiently. I won't go into details. But each one has its place. FPGA has its place, GPU has its place. It's not like one is always better than the other. So there's ways that we can think about data processing that's different than what's done before. And it's also important to think about how it's going to scale in the future. And a direct imaging architecture using like FPGA, in our assessment, can scale very well with a larger number of elements, larger bandwidth, or forming a larger image like a megapixel image, or so on. And this is a cost estimate, like if we were to install these such FPGA systems, direct imaging systems on all the SKA low stations, for example, our estimate of the cost is it's going to be a small fraction of the total SKA cost. So it's not extremely bad either. So these are some of the technological opportunities that we have as we go forward with data-intensive astronomy in the SKA era. Now I will switch to more conventional topics. Imaging, for example, we've had significant developments in the last 2 decades. Some of the significant developments are highlighted here, dealing with non-coplanarity, the W terms, and the heterogeneous array systems, antenna terms, the A terms, and dealing with wide fields and large curvatures. Very innovative algorithms like W projection, W stacking, W clean, WS clean, etc. And as there's also new developments in the works. Some of which are listed here. I won't again go into details. This is the image domain gridding is a very efficient implementation of some of these effects. When we look at wide fields of view that are typically a big fraction of the entire hemisphere, then there are some much more natural basis for imaging, such as spherical harmonic imaging, M-mode imaging, and so on, which are much more natural to work with than a forced Fourier basis. And of course, a lot of machine learning methods, I think, are going to be coming up soon. They've shown extreme promise. This is, for example, one example of the difference that we could make between conventional to machine learning-based methods, but they are yet to become production scale, so that's going to be an important step going into the future. Calibration, of course, is always going to be challenging at low frequencies. Well, in general, we have situations why calibration is challenging. Either the signal is weak or has a very high dynamic range requirement, such as the EOR. And so this applies to low frequency dense aperture arrays, for example. Or when you're dealing with low signal to noise measurements, very sparse aperture coverage, where there's not much information to work with. And this would apply to VLBI, for example. So this is another area of challenge, or you could take it as an area of opportunities. So this is a little bit about my own work in this area. So again, I've been fascinated by these approach of calibration independent processing. And again, employing the use of closure quantities, closure invariants. These are known to be calibration independent to first order. Of course, the most popular ones are closure phases and amplitudes, but there are a whole class of closure invariants that we could make use of. And just to point out, the number of closure quantities is always going to be lesser than the number of visibilities that you have. So one could argue that we will not capture as much information. But in terms of information ratio, if you look at the number of closure quantities we have and the number of visibilities you have is of order 1 minus 2 divided by n. And when n is large, this is pretty close to 100%. So you have all the information that you would want, almost all the information. So of course, how we process them is going to be interesting and different. Here's an example of a VLBI EHT style work that we've been developing. As you can see, it's a very sparse array, quite a bit of gaps here. So it's information sparse here, information poor. And our idea is to independently reconstruct the EHT results just using closure quantities, calibration free. And so we are employing a deep learning network to work with the closure quantities that come out. And you can see that at least these are samples drawn from the untrained classes. And you can see that the reconstruction that we get on the right side is pretty spot on for the amount of information that the sparse information that we're working with. So of course, this is VLBI, may not apply to SKA and so on. It's simpler images. So with SKA or EOR, it's going to be much more complex fields. But then the amount of information and visibilities is also correspondingly larger. So I'm sure that we could, in principle, try these calibration-free schemes to get at what we want if we put some effort into it. Now, of course, RFI is going to be a ubiquitous problem everywhere. And site selection is very critical for terrestrial-based RFI, but even that is becoming irrelevant with the options shrinking fast with satellite-based RFI here. And so obviously going to the lunar far side is an option, but can we do something better with what we have that is ground-based? There's several different options we could explore. If you're thinking of beamforming-based antennas, then we could explore innovative spatial nulling techniques. There's also, I think this is going to become very significant and important, have a significant impact, is online real-time RFI detection in the digitized samples and doing some pre-correlation flagging and then correlating the cleaner samples. There's an example of the RFI strategy that's almost done, just one more. RFI strategy that's being implemented on the GMRT. And as you can see, the statistics change and they make a big impact, at least on the short baselines for the moment. So this might make a big difference while we are still ground-based. So this is my summary slide. So we have put in decades of innovation to get to this point where we have the SKA, but also in the meantime, the requirements have also grown significantly from the point of view of data volumes, data rates, dynamic range, sensitivity, sparse measurements of information, especially when you're looking at high time resolution, wide fields of view, and so on. So I believe that the current techniques, algorithms, and instrumentation need to scale more sustainably, and that requires new ways of thinking, not just for SKA as it is now, but we need to think beyond the SKA. And I think based on some of the examples I've shown, there's a lot of opportunities for innovation. Okay, I'll stop there and take questions.
Very interesting. So in terms of epics, right? If you do the right direct Fourier transform of the voltages, of course, you're including the autocorrelations as well, right? And the autocorrelations historically, right, we've thrown away because, right, they have all the electronics,
right,
garbage in it, so to say. So in how far do you see that here, and is it affecting the results, or do you have a mitigation strategy for that?
Yeah, there is a mitigation strategy, and it's quite simple here. So for instance, this is an image form. If the average will not be 0, that means there's a DC term here. So we could form these images, and typically, if you're going to inverse Fourier transform it back to visibilities or something, most of that autocorrelations would be at the 0th pixel in that. So we could, at a slower cadence, transform it back and remove that at whatever cadence that we are interested in. So that won't cost the same cost of this FFT, but it's at a slower cadence. So it's possible.
Maybe just, it's not a question, but a comment. So on this image domain gridding, we've tried this because many of these experiments are going wide field, and you'd want to do forward simulation. It's extremely expensive if you do GFTs or other techniques. So, but we did the hard work on image domain gridding. We compared it to Sage-Cal and direct Fourier transform point source, and we do find that image domain gridding still has errors in it that we don't fully understand, that exceed the 21 centimeter signal. I mean, it's very, very fast, but if you do techniques that we have like Sage-Cal and do forward predict and direct Fourier transforms, they are the same within numerical precision, but the image domain gridding is not yet.
Okay.
So there's still some shortcuts or things in that process that
I'm sure there is,
lead to some errors. Yeah. But it's very interesting because it's very fast.
Yeah.
Thanks.
Thanks.
Just a couple of quick questions because. So your closer phase power spectrum, that is pseudo millikelvin square, right?
Yeah.
So you lose absolute calibration. How the image will look like image, what would be the unit of the image?
It's hard to interpret it as image closure phases are hard to interpret. I mean, there is some interpretation, but in a complex field, it's going to be hard to interpret it physically. I've shown pseudo millikelvin square because there is some level of, when you have a overwhelmingly bright signal, such as the foregrounds, and it's a small fluctuation, you can treat these fluctuations as linear. And so you can scale it with some kind of a weighted average of these visibilities as the scaling factor. So that's why we get the pseudo millikelvin square, but the interpretation will require a lot of forward modeling and seeing what we expect for a whole part of the parameter space.
Hi, very interesting work. I have a question on the EPIC again, actually.
On the?
EPIC, the direct imaging. So how do you, I understand that when you do this, so you do not have, your images, you do not have any more individual antenna voltage. So how do you deal with calibration in this case?
Yeah, I didn't speak much to it, but there is this branch, this feedback branch that does the calibration and applies it on the channelized voltages. Basically, as the data is passing through, we have, let's say we've sort of half converged to a calibration solution, and then we want to refine it further. So we could take the model of the visibilities, but the visibilities are not formed here, and then compare it with some calibrator pixel, correlate the incoming voltages with that calibrator pixel. That will give you the current set of visibilities and you model set of visibilities from before, and you could work out the gains from there. So it could be applied back on this before it goes into the gridding. So scheme, in principle, it works, but it doesn't have to go super fast. So the complexity of the calibration is much slower. Yeah.
Last very quick question.
Quick one. So the closer phases that you talked about, so if you have polarization leakage, then the closer phase is affected by that. So how do you?
Yes, yes. So we have, that's why I kept saying that these effects are eliminated to first order, but there will be second order effects of the kind. So, but there is a different set of closure invariants to deal with that, that are robust to polarization leakage as well. So one would have to go a bit beyond the standard closure products. Yeah.